I'm going to begin section 9.2 and where it says estimating a population mean. That's where 9.2 would begin in our notes here. So we've been constructing confidence intervals about a population proportion, and we're now going to construct confidence intervals for a population mean. X bar is the best point estimate for the population mean mu. The idea is this, similar to what we were looking at in the last section. We want to build an interval of numbers where we think mu is going to be located. Here's an example. A researcher for the Federal Aviation Administration wishes to estimate the average flight time on American Airlines from Albuquerque, New Mexico to Dallas, Texas. The researcher selects 14 flights and records their times in minutes. The mean flight time for the data that was obtained was 103.4 minutes. Okay, suppose that we wanted to know the parameter and the point estimate in the study. The parameter would be the average time that it would take all American airline flights from Albuquerque, New Mexico to Dallas, Texas, which is something that we would never know since there's no way to track every single flight that has ever occurred from Albuquerque to Dallas. Okay, so we're not going to know the parameter, but the point estimate would be the sample mean that is from the 14 flights that were studied here. The average time with these 14 flights was 103.4 minutes. Okay, now, if we were to look at all the flights that have ever occurred from Albuquerque to Dallas and compute the average, it probably wouldn't be 103.4. Maybe it's going to be around that number, ideally. But we'd like to, build a range of numbers where we think that mu would be located. Or, that's the idea. There's a note here. Remember that the population mean, mu, is unknown. Confidence interval estimates for mu are of the form x bar plus or minus e. E is the margin of error, x bar is the point estimate. In general, you always take the point estimate and then add and subtract the margin of error. The margin of error is represented by z sub alpha divided by 2 times sigma divided by the square root of n. Now there's a problem with this because in order to construct a confidence interval by hand, we would need to know the population standard deviation, sigma. In reality, this is very unlikely that we would happen to know sigma and not mu, okay? Because mu is involved in the formula for getting sigma, right? Now, I guess it could happen, but that would be very strange to happen to know the population standard deviation and not know the population mean. Now, to fix this problem, we could use the sample standard deviation S instead of sigma, but that actually creates another problem because S is going to vary from sample to sample, right? And we need one number. We don't want something that's going to change from sample to sample. The distribution of the sample means is also no longer normally distributed, so it wouldn't make sense to be doing anything with z-scores or the normal distribution table, okay? And so there's several problems here with what's going on in just changing sigma to s. So a new model must be used to determine the margin of error that accounts for this additional variability. Definition. Suppose that a simple random sample of size n is taken from a population and x bar is the sample mean and s is the sample standard deviation. If the population from which the sample is drawn follows a normal distribution, then the distribution of t, and how we calculate t is we take x bar minus mu divided by s over root n, follows what's called the student's t distribution with n minus 1 degrees of freedom. Okay, there's a note there. For these problems, the sample size is usually referred to by giving the degrees of freedom n minus 1. So if you have a sample of size 57, there's going to be 56 degrees of freedom. In general, the degrees of freedom are always one less than the sample size. The term degrees of freedom is used, an example for the terminology here. Suppose that, if you have n observations, okay, n minus one of them have a freedom to be whatever they want, okay, but the nth value has no freedom. So like, as an example, if you had 6 donuts in a box and 6 people are each going to select a donut, the first 5 people have a freedom of choice for which donut to pick, but the 6th person does not, since the 6th person would have to get the last donut in the box, whatever that is. Okay, so that would be 5 degrees of freedom in that particular problem. Let's go to the next page and we'll look at some properties of the t-distribution. The t-distribution looks very similar to the normal distribution, in that we're working with a bell curve here, but it actually shows more dispersion and is different for different degrees of freedom. It is bell-shaped and symmetric about the mean, just like the normal distribution is, and the mean, median, and mode are all 0, okay, in a perfectly shaped distribution. Of course, we've already learned that in the case of a normal distribution, most of the time it's not going to be perfect, okay. But the 0 is going to be at the center of the distribution there, and the area under the entire curve has to be 1, just like with the normal distribution, okay. The mean is in the center, so the area to the right of the mean is 1/2. The area to the left of the mean is 1/2. So these are all properties that are very similar to what we've already talked about. The 2 tail ends of the curve get closer to the x-axis, but they'll never touch the axis. Also, the area in the tails of the t-distribution is going to be greater than that of the standard normal distribution. Okay, this is because now I've got some curves drawn here, and here's where t is the t-distribution when n is 5, the t-distribution when n is 15, and then you got the standard normal density curve. As the sample size increases, the t-distribution approaches the standard normal distribution. This is because n gets larger, so you have more information in front of you. That's a good thing, and therefore the sample standard deviation is going to be closer to the actual standard deviation. Okay. Now there is more dispersion underneath the t-distribution under the tails. That's what this note was talking about there. But you can see that as n is increasing, we have this t-distribution curve is going to look very much more like the standard normal density curve. There's another note here which says, in the unlikely event that we would happen to know sigma and not mu, that would be very strange, but I suppose it could happen, then we would be constructing z intervals and not t intervals. Okay. Now, we're talking about confidence intervals. In this section, we're going to be using the student t-distribution, and so these confidence intervals are called t-intervals. Okay, and the idea is that we don't know mu. We're trying to figure out where mu is located, but also we are under the assumption that we don't know sigma. Okay, if we did know sigma, we would not be doing the information presented in this section. We would be constructing a z interval, and the formula is different for doing that. So something to keep in mind. Now, I've got the steps for constructing a 1 minus alpha times 100% confidence interval about the population mean, where sigma is unknown. Okay, suppose that a simple random sample of size n is taken from a population of size capital N. It must be the case that the data comes from a population that is known to be normal, or the sample has to be something that is at least 30 to construct the interval. Because of what we had talked about in the last section, if the sample is big enough, then the sampling distribution about the mean is at least approximately normal, if the original population was not normal. Otherwise, if the original population is normal, then there's no problem. You're already working with a bell curve. Also, the sample size must be small relative to the population size. That is no bigger than 5% of the population size. Okay, and if a sample is given, we're going to use the raw data to compute the point estimate, x bar, and the sample standard deviation, s. In some of these problems, they'll give you a numerical summary that you'll be using, and then on some other problems, they'll be giving you the raw data, and we'll look at those two situations, and I'll show you how to get the results on the calculator. And we'll determine the interval, then would be the last step. There's another note. To find the area under the t distribution, there's a table, kind of like the table that we had looked at with the standard normal table here that we've used quite a bit. Okay, there's a t distribution table, and that would be a necessary thing to have if you were to construct confidence intervals about the population mean by hand. Okay, we're going to omit using that table though, and we're going to focus on finding these intervals by using the calculator. Okay, so just like what we were doing with a population proportion, you know, there is formulas in the book, but we don't need to be formula heavy here at the moment. We're going to have the calculator do a lot of the dirty work. Okay. Let's do problem 7, and then we'll break here. Problem 7, a 90% confidence interval for the mean number of hours that full-time college students sleep during a weekday was found to be 7.8 to 8.8. What is the point estimate? Well, the point estimate is always the middle value on the interval. You see, you're using the point estimate and then adding the margin of error to build the interval. Okay, so the question here, what number is right in between 7.8 and 8.8? Well, that'd be 8.3. So x bar, the sample mean, that's our point estimate, would be 8.3 hours. Okay. The margin of error would be a half hour. If I take 8.3 plus 1/2, I get 8.8. If I take 8.3 minus 1/2, I get 7.8. So I'm adding and subtracting the margin of error to 8.3 to get these endpoints here on the interval. Part C, interpret the interval. So this is a 90% confidence interval. What that means to us is that we are 90% confident that the mean number of hours that full-time college students sleep during a weekday is between 7.8 hours and 8.8 hours. Okay, and again, you'd want to be specific, you know, indicate that we're talking about full-time college students, you know, part-time students might be different. Also indicate that we're talking about a weekday, a weekend might be different, you know, so be specific about what the interval means here, you know, in general.